Closing the system and creating artificial agents. This is a fairly abstract lecture, but it goes to the core and the potential and the limitations of artificial agents. And the title indicates what we do all the time. We close the system. So, a first question is, what is an artificial system? And before we can answer that question, we have to address the question, what is an algorithm? Well, there are lots of different definitions of algorithms, but a useful one for our purposes is that it is a finite sequence of well-defined instructions that lead to an intended outcome. So, what is an artificial agent then? Well, that is simply an implemented algorithm that enacts the algorithm in the real world or in a computer world or something like that. So the next question is then, how do we create an artificial agent? And that actually means that how do we create something that acts predictably and as intended? So where can we start with that question? Well, maybe we should start in the real world, in the general world of systems. And what is a system, or what is the defining property of a system, is that it has characteristic dynamics due to stronger internal than external interconnections. So what does it mean? It means in order to be a system, you have to be somewhat isolated from your environment so that you are different from your environment. And how can you be different from your environment if you are not fully or differently connected to the environment? You have fairly strong internal connections and not so strong external connections. And that leads to characteristic behaviors. So let's go to a typical general example of a system. So here we have a system that has fairly strong internal relations, like we said, and relatively weak external relations. It must have external relations because it is embedded in the world. It can be a rock, for example, and this then here might be in the shade of the rock, and the rock influences via its shade its environment and whatever is happening in its environment. These are all components that are also systems in the system, and these are other subsystems of the environment. So this is kind of a general depiction of a system in its environment. So let's go to a number of system properties. Well, a system, in order to be found useful, it should persist for some time. And that means that it either changes slowly or it has some stabilizing dynamics. So that means that if it is perturbed, it is robust, and that leads to a form of stability that leads to persistence through time. Another thing is that it has characteristic properties and characteristic dynamics, and that defines what class or what type of system it is. And with knowledge of its dynamics, it can be predicted how it will respond and how it will develop over time. And at the same time, it has characteristic properties and dynamics that can be enforced by a user, for example, and it can also be recognized because it has something characteristic. We have two completely different ways of conceptualizing the same physical system. We can either see it as a closed system and treat it as a closed system, or we can treat it as an open system. And when we treat it as a closed system, we assume that its context and its function can be fully accounted for by an input-output relation. And that means that we assume that the whole system is effectively disconnected from the rest of the universe. But we can also have an open system, and an open system is in constant interaction with its environment and in constant development. And there is constantly a flow of mass and energy through the open system. Open and closed systems are extremes in looking at particular parts of the real world. So the universe is the only truly closed system. It has no in and out flows and no information exchange with the outside. If it would have information exchange with the outside or in and out flows with the outside, they would be part of the universe. So per definition, it is closed. But all normal systems, they are open, and they are intimately and essentially embedded in an environment and subject to uncontrollable environmental influences. And they are effectively infinite. A closed system is different. There is a designer approximation. And the designer approximation is something like, suppose we have only these in and outputs. And this is an approximation that needs to be maintained. And that effectively entails that you need to control the environment. And also you need to guide the characteristic dynamic properties in such a way that they are so constrained that they produce the desired output. And in all practical manners, that this entails that we have a finite set of states of a closed system. And in principle, they are fully knowable, and because they are fully knowable, the output can be predictable. Let's look again at open and closed systems. For a closed system, the context can be fully accounted for via an input-output relation. And we can do that because we actually protect the closed system from outside influences. So we build a border kind of around it. And that leads to the notion of controlled input. And so what is controlled? Actually, it is whatever is going in the system that is really controlled. And because the system now has only the influences that we allow it, it has predictable output. So we're not saying anything about what the output actually is, but just that it is predictable because it has no choice than to follow the input coming from the outside, which is now under our control. Yeah, and this is something that a designer of the system does. So what now is an artificial agent? An artificial agent is an implemented sequence of well-defined instructions with intended input-output behavior. And it can do so because it is protected from all kinds of outside influences. So now the question is, how do you curtail and proscribe system dynamics? So let's go to two extremes of controlled versus innate dynamics. On the right, we have the natural dynamics of turbulence in a common vortex street. And the key thing is that it's always kind of irregular, it is dynamic, it is less precisely predictable, and every pattern is unique. But still there is a lot of structure, and the thing can only do a particular type of behaviors, the innate behaviors, and that we show here. So that there is a lot of structure, but it's never completely repeatable, etc. And then we have the example of an electronic circuit board that is designed to function in a particular way. It has regular structures, it is static, it is much more precise in terms of what it does, and many patterns are also repeated, while there is no pattern repeated here. And what we want to do, if we want to create an artificial agent, is somehow curtail the innate dynamics, here visualized as that vortex street, into something that looks more like the electronic circuit board. And we as humanity are very good at that. So our cities are typically shaped, while our nature that is allowed to self-develop, and it leads to completely different structures. Again, irregular, more dynamic, less precisely predictable, and every pattern is unique. And while the opposite holds for the controlled environments. So we start with a semi-closed system, and that semi-closed system that has its innate dynamics, and there are influences on the system, and then there are influences by the system on its environment. And as a system, it has stronger internal relations than external relations, but we visualize them here. And because it is kind of partially decoupled from its environment, it has innate characteristic properties and dynamics. And we can go two ways. We can try to liberate the system from its limitations, whatever limitations it has, and that promotes its innate dynamics. Or we can go the other way, where we control the environment and curtail its innate dynamics. And that is the way we are going here. So our system, and how can we close the system, curtail it, by imposing more and more different conditions on it. And what do I mean with that? I mean that we ensure that only particular input can actually come into the system. And we basically say, if the input complies with this, and with this, and with this, and with this, so if condition 1, 2, 3, and 4 are true, then we allow it into the system. And that closes the system and also makes it predictable. The more we impose conditions, the more curtailed its innate dynamics is, and the more predictable it is going to become. So that closing of the system, and that is very important, that is an act of the designer. The designer closes the system, ensures that it is only exposed to a particular type of input, and after the designer has done his job, then it is the user who controls the environment of the system by basically playing the game of the system, by only exposing it to a particular type of input. And this together ensures that a system can be approximated as isolated from the rest of reality. So it is only exposed to what the designer wants it to be exposed to and what the user allows it to be exposed to. And that ensures that the system is only able to do whatever it is supposed to do. And that leads to the predictable output of a closed system. And why do we do all this? That is to create that predictable and dependable utility. We want to make a system with a particular function, and then therefore we basically close the system. We make it more and more predictable by closing it further and further. So let's go to a highly controlled system, in this case an iPhone, for example. So that has also its input, it has predictable output, and it is a closed system with predictable dynamics. We do this because it has predictable utility, and in humans we want to use predictable utility typically for high-stake problem solving. So you want to have something that you can really depend on in difficult situations. And predictable utility is only possible in familiar situations. That is also important, because if you're in an unfamiliar situation you cannot have predictable utility. Then there is a short-term view of the type, if this is the case, then that holds. And you can only do that if you are there to control the system. So it's always short-term. Then it is about a known and finite set of inputs, a finite set of internal states that you might know or not know, and definitely a finite set of outputs. And that defines the system. And that system is completely unaware of its environment because we have made it unaware. It is only aware of what we expose it to. Well, the high-stakes problem solving leads to only one solution. We focus our attention on doing something of a particular type, and we want one particular solution. Well, another thing is that we close the system by ensuring that conditions are either true or false. And that entails that we have a class of situations where the condition is true and another class of situations where the condition is false. And that leads to a binary classification. It's either this, the true thing, or that, the false thing. And that makes the system insensitive to within-class differences. You don't care if it is one way of being true or another way of being true. It is just true, and that's the only thing that you really care for. And that leads to categories of things or objects or categories in the world associated with true or false. And that leads to useful categories that you can use to say it is true or it is false. And it also kind of informs the worldview of the system. In practice, systems or agents or artificial agents are part of a nested system. And in this case, we show a multiple of those systems with all predictable behavior, all controlled input. And in this case, they are organized in a particular structure, kind of a syntax. And the output of this thing is even more constrained, because now we have all the systems that constrain each other even further because they all produce predictable output. And it leads to very clear observable effects. And for the outside observer, it leads to something that's objective. You can just say, oh, if this is the output, then it is like this, and for everyone, every observer, this is exactly the same. So that leads to shareable objective meaning of the system. Another thing is that if you look at the different parts of the system, they kind of predict how the whole will work. So the parts lead to the whole. And like I said, we have been suppressing influences and ignoring context. So this whole system can only deal with whatever it is designed to deal with. So we have even more properties. Order and structure lead to syntax, part lead to the whole. It needs to be controlled. There are all kinds of observable effects that lead to shared meaning, and we need to isolate the system by suppressing influences and ignoring context. But this is also very much the world of AI. The world of AI is very good in working with familiar situations, stuff that it is designed for, stuff that it has seen in while it was trained or something like that. There is always a short-term view. There is no long-term view, basically because it hasn't been put into the system. It is either this or that, and it's basically guided by if this input, then that output. It is completely unaware of its environment. There is a lot of order and structure and a syntax that basically defines the whole system. There is not really meaning in the system, there is structure in the system, syntax in the system. Well, whatever it produces in terms of observable effects, that always leads to the same shareable meaning of other people or other observers of the system. Everyone kind of agrees on what the system produces as output. For example, a word or whatever, a certain action. It is also a one solution type of thing. That can be very complex, but it does a particular thing and not something else, and it leads a particular type of output via a particular way. Its environment needs to be controlled by the designer, ensuring that particular things can go in, but also by the user, by ensuring that the system is exposed to something that it can actually deal with. It is seeing the world in binary type of things. So that means that it is insensitive to within class differences, and it sees the world as useful categories that either make its conditions false or true. So this is the world of AI, and it was the result of closing the system. But the really interesting question is, what did we lose while we were closing the system? What did we define away while we were closing the system? And what is unachievable now due to closing the system? Yeah, so we gained a lot. We gained predictability and a particular function, but we lost also something. So that is the key question that we are going to address later.